Welcome to G Fun Facts Online. Today, we're talking about something that sounds like it breaks the laws of physics. We all learn in school that if you heat a solid to its melting point, it turns into a liquid. Ice melts at 0 degrees Celsius. Iron turns to molten liquid at about 1500 degrees. These are fundamental facts. But what if I told you that in specialized labs, physicists are taking solid metals, like gold, and heating them to temperatures hotter than the surface of the sun, all while they defiantly remain solid? It's not science fiction. It's the strange and counterintuitive world of superheated solids, a phenomenon that's redefining our understanding of matter. To understand how a solid can stay solid far beyond its melting point, we first need to talk about a concept called a metastable state. Think of it like this. A book lying flat on the floor is in a stable state. It's at its lowest possible energy level. But if you balance that same book on the very edge of a high shelf, it's in what we call a metastable state. It's stable for now, but any small disturbance, a slight vibration, a gust of wind, will send it tumbling to its more stable state on the floor. A superheated solid is just like that book on the shelf. It's trapped in a temporary state of stability. The liquid state is the floor. It's the lower, more stable energy configuration at that high temperature. But the solid is stuck in an energy valley, shielded by a barrier that prevents it from immediately turning into a liquid. So why doesn't it just melt? The answer lies in how melting actually begins at the atomic level. The common theory is that as you heat a solid, its atoms vibrate more and more violently until they break free from their rigid crystal structure. But this transition isn't instantaneous. It needs a starting point, a seed for the liquid phase to form. This process is called nucleation. For a solid to melt, a small cluster of atoms has to first break away and form a tiny liquid droplet, or nucleus, within the solid. Creating this nucleus takes energy, specifically to form the new surface between the liquid and the solid. This energy requirement acts as a barrier. In the real world, this barrier is tiny because metals are full of imperfections. They have surfaces, grain boundaries, impurities, and tiny defects in their crystal structure. These imperfections act as catalysts, or easy starting points, for liquid nuclei to form. This is called heterogeneous nucleation, and it's why your iron skillet always melts at its predictable melting point. It's got plenty of spots to get the process started. But what if you could eliminate all those starting points? What if you had a perfect, single crystal metal with no defects, no surfaces, no impurities? In that case, the material would be forced to melt from within its perfect structure. This is called homogeneous nucleation, and it requires overcoming a much higher energy barrier. To push the atoms over that huge barrier, you need to pump in way more energy, which means heating the material to a temperature significantly above its normal melting point. So, the entire science of superheating a metal is really a quest to prevent the easy kind of melting and force the difficult kind. How do scientists actually achieve this? The key is speed. The challenge is to deliver a massive amount of energy to the material so incredibly fast that the normal melting process doesn't have time to kick in. The game changer here has been the invention of ultrashort-pulse lasers. These lasers can deliver an intense burst of energy in a time frame of femtoseconds. That's a quadrillionth of a second. To put that in perspective, there are more femtoseconds in 1 second than there are seconds in 30 million years. This ultra-fast heating process creates an energy shock wave. The laser energy is first absorbed by the electrons in the metal, which then transfer that energy to the atomic lattice, causing the violent vibrations that lead to melting. But it all happens so quickly, at a rate of about a quadrillion Kelvin per second, that the atoms simply don't have time to organize into liquid nuclei at any potential defect sites. The heating literally outruns the melting process. To make this work, you also need an absolutely pristine sample. Any contact with a container could introduce a nucleation site and ruin the experiment. So scientists use clever levitation techniques. One method, aerodynamic levitation, uses a jet of inert gas to suspend a small metal sphere in mid-air. It just floats there, untouched, while the laser blasts it with energy. Of course, you can't just stick a thermometer into something that exists in this state for a few trillionths of a second. So researchers use advanced diagnostic tools. One of the most powerful is called inelastic X-ray scattering. They fire a pulse of extremely bright X-rays at the superheated sample and analyze how those X-rays scatter off the vibrating atoms. By measuring the change in the X-ray's energy, they can calculate the speed of the atoms, and from that, the material's precise temperature. They can also use diffraction techniques to confirm that the atoms are still arranged in a perfect crystal lattice, proving it is indeed still a solid. For decades, there was a theory that set a hard limit on how hot you could make a solid. It was called the entropy catastrophe. Entropy is a measure of disorder, and liquids are naturally more disordered than solids. The theory stated that you couldn't heat a solid to a point where its entropy would become higher than the liquid version, as this would violate the laws of thermodynamics. This theory predicted a temperature ceiling for superheating, roughly 3 times a material's melting point. But in a landmark experiment, this long-held theory was completely shattered. A team of scientists at the SLAC National Accelerator Laboratory used their powerful lasers on a thin film of solid gold. They managed to heat it to an astonishing 19,000 Kelvin, that is over 33,000 degrees Fahrenheit, or 18,700 Celsius. This is more than 14 times the normal melting point of gold, and for a fleeting 2 picoseconds, 2 trillionths of a second, the gold remained a solid crystal. This result blew the entropy catastrophe theory out of the water. The secret, it seems, was the sheer speed of the heating. The laser pulse heated the gold so fast that the material didn't have time to expand. The original theory assumed expansion would happen, but by outrunning it, the scientists pushed into a completely new regime. This stunning result proved that the limit for superheating is far higher than anyone imagined, and it might not even exist if the heating is fast enough. So this is fascinating physics, but what are the real-world applications? Why spend so much effort to keep metal solid for a few trillionths of a second? The potential is enormous. First, let's talk about advanced materials. By having this level of control, metallurgists could create novel alloys with unique microstructures that are impossible to make with conventional methods. Imagine heating an alloy just past its melting point, allowing some atoms to rearrange, and then cooling it back down before it liquefies. You could create materials with unprecedented strength, ductility, and resilience. This could lead to more efficient jet engines, lighter and stronger components for spacecraft, and safer nuclear reactors. Speaking of nuclear reactors, this research is critical for the future of fusion energy. One of the biggest challenges in building a fusion power plant is finding materials that can withstand the incredible heat and radiation inside the reactor core. The walls of a fusion tokamak will be subjected to conditions similar to these experiments. By understanding how metals behave at these extremes, we can design new tungsten-based alloys that won't degrade under the blistering temperatures of a fusion reaction. The applications even extend beyond Earth. The interiors of planets and the atmospheres of scorching hot exoplanets are places of extreme temperature and pressure. On an exoplanet named WASP-76b, for instance, astronomers believe it gets so hot that it rains molten iron. Our lab experiments with superheated metals provide a way to test and understand the physics of these exotic environments right here on Earth. Fundamentally, these experiments are pushing our most basic theories of matter to their absolute limits. By forcing materials into these extreme states, we learn more about the forces that hold atoms together and the intricate dance of phase transitions. This foundational knowledge is what all future material technology will be built upon. The road ahead is still challenging. These experiments are technically demanding and expensive. Scaling up from tiny, nanometer-sized samples to industrial volumes of material is a huge engineering hurdle. And scientists are always in need of even more precise tools to probe these fleeting states of matter. But the journey has just begun. Researchers are now eager to see if other materials can be pushed to the same extremes as gold. They are asking a fundamental question: is there any limit at all to how hot you can make a solid? We are witnessing a paradigm shift in materials science. The solid ground of classical thermodynamics has been shaken, and in its place, a new and exciting landscape of physical possibility is being revealed. Thank you for tuning in to Fun Facts Online.